Okay, this is lesson 3.5, Transformations of Exponential Functions. At this point, you've already done a graphing assignment that gives you a good idea of what different transformations look like with regard to exponential functions. We're just going to draw a few of them here to get our heads back in that game. So, this guy is a vertical stretch and a vertical reflection, or a reflection in the x-axis. So it's going to be the same picture, except it's going to, you can do it two different ways. You could flip it first and then make it grow, in this case negative, twice as fast, or you can kind of imagine that it starts to look like this and grows a lot faster than the blue one, and then flip it. In either case, it's going to be tighter to the x-axis for longer, and then it's going to turn more dramatically than our blue graph. And there we have it, a vertical reflection and a vertical stretch by a factor of 2. Okay. Again, I didn't draw one, but you could have a horizontal stretch compression as well if you had something out in front of this exponent of x. Okay. Again, in the middle, the blue one is y equals 3 to the power of x. What happens if I tack on a minus 4 to that thing? I'm just moving it down 4 units. Okay, so I can pick a few key points, or I can kind of pick this asymptote and say, all right, now my asymptote is going to be down here at -4, and I'm going to try to do the exact same drawing, pretty much something like that. Okay, and again, the arrows should really be going in both directions. And our last one, this is, again, this transformation is just affecting the x, so it's a horizontal transformation. It's addition and subtraction, so it's just a moving of the graph left or right. This is going to be a horizontal translation right 2 units to the right. So what I could do is I could take a few key points on this thing. Let's say I take a key point here and here and here and here, and I'm just going to move them over 2. And then I'm going to draw my nice smooth curve through those points. It's going to be the exact same shape. It's just curling up 2 units later. Okay, brief introduction to transformations of exponential functions. Let's dig into a harder example, which is there for you on page 17, example 1. Okay, here is our transformation parameters, and conveniently for any function we kind of use the same letters, right? C is going to be a vertical translation up or down. C units, D is going to move left or right, D units. K is a vertical stretch or compression horizontal by a factor of 1 over K. And A is a stretch, compression, reflection vertically. So there's the same letters that we use for the other functions, and we have it broken up for us here. So we want to identify what are each of these pieces going to do. So I notice that my parent function, the parent function in this scenario is going to be y equals 2 to the power of x. And we're basically saying, okay, what has happened to this in order to create that? What is this going to do? What's that negative sign going to do? Okay, it's a reflection.
It's also going to multiply divided by 2.
Reflection in the x-axis. And I don't need to worry about the 2 because I've identified that my parent function is 2 to the power of x. So the 2 is not different from 2 to the power of x. So on my first graph, we're going to graph 2 to the power of x, and then we're going to do a couple of transformations to it. What about this guy? This little number 2 up there. What does he do?
It's a horizontal stretch or compression.
Yep, that's going to be a horizontal compression by a factor of 1/2. And then our last two we're going to do together. Our last two we're going to do together. They are just the shifts. Okay, it's a shift right 3 and shift up 5. Alright, so step by step we're going to make that happen on our graph. I'm going to draw our parent function, y equals 2 to the power of x to the best of my ability. It's going to look something like this. And the first thing that we're going to apply is the horizontal compression. So we've got our blue here. We're going to do a horizontal compression by a factor of 1/2. That means every single point along this curve is going to be pulled in half the distance from the y-axis. So you could do it with a table of values. Right now we would just kind of pick a few key points. For instance, we know that some of the key points on here are 1, 2, and 2, 4 is on here, and 3, 8 is on here, and 4, 16 is on here. So if you have those numbers on your grid, it's really easy. I'm just kind of guesstimating where those are, and then basically what we're going to do, because it is a horizontal compression by a factor of 1/2, it tells me that I'm going to need to cut the distance between each of those points and the x-axis in half. If you have nice squares to do this with, you can basically just work from a point on the curve to the left and cut it in half. Not super difficult if you have the graph in front of you. That works for the right side of the graph. It also works for the left side of the graph. So you can see how this thing is going to change. It's actually going to stay lower longer, and then it's going to curve up more quickly, more significantly. So the only thing that we have applied here is the horizontal compression by a factor of 1/2. So I'm going to name my graph here. All I did was took 2 to the x and made it 2 to the power of 2x. Okay, that's the only transformation we've applied so far. Next, I'm going to reflect it. Okay, so I'll take my red because that's the arrow that I drew for it here, and I'll draw what we have. Our new graph was in blue. Looks kind of like that. And now to apply, so again, you can name that one. That one is y equals 2 to the power of 2x. And now we're going to reflect that over the x-axis. So it's going to look like that. And I'm going to name it y equals, the only thing I applied in this step was a negative sign out in front, so we have negative 2 to the power of 2x. Okay, I'm going to copy that one onto the last graph that you have there. Try to make it look relatively the same. It's easy for me using a few different colors. That was y equals negative 2 to the power of 2x. And my last transformation is going to be a horizontal and vertical translation. So I did that in purple. I'm going to move my asymptote from being the x-axis. I'm going to move it up 5. So I'm just going to draw that asymptote for myself to give myself a reference line. And we're going to move this thing to the right 3. Okay, that's kind of, for me, I don't have squares, so it's just kind of hypothetical. You have squares, although you're not going to necessarily be able to use a scale of 1 block to 1 number because I didn't give you enough boxes to do that. But you could do, on your Y scale, you could do 2, 4, 6. Then you'd have enough room. At any rate, we're moving it up 5, and then to the right 3, sorry. So wherever I am here, I'm going to be moving all these points over 3-ish. Up. And then where my red one starts to curve right here at the y-axis, my purple one is not going to start to curve until I get to about 3 out here. And then starts to curve, and it should hold the exact same shape as the red guy. Something like that, with an arrow on both ends, and label it. That is the graph y equals -2 to the power of, and I applied both of my other translations, so I've got 2 bracket x minus 3 close bracket, and then the end of all that plus 5. Okay, so that is applying a transformation to an exponential function by hand, kind of going step by step. We used 3 drawings to do one thing. You could do it all on one graph and then just kind of highlight your new one that you have, but this was easy to break it up this way. Alright, example 2, circuit analysis. In a particular circuit, the current, I, measured in amperes, after t seconds, can be found using the formula I with respect to t is equal to 0.9, and then in brackets 1 minus 10 to the power of negative 0.044 t. We're not expected to know how to graph that, or to give it a shot, but we are going to graph it using graphing technology. So I'm going to pause the video, we're going to look at this thing on Desmos, and then we'll answer the questions there. If you've drawn that out, we can start to answer number A to get a good window to view this thing in, but so the first thing we're worried about is the domain, and we're talking about current and electricity, and the domain is it's the current with respect to time. So time, we're not going to have negative time. So the domain is t belongs to the set of real numbers such that t is greater than 0. And now we can go ahead and look at what the current is in the circuit after 2 seconds and then after 5 seconds. And all that really is going on Desmos, finding the x value or t value of 2 and finding out what the value of the function is at that point. So let's do that. Alright, on Desmos we found out that the current after 2 seconds is 0.165 amps. And the current after 5 seconds is 0.358 amps. And then C, I'll just draw a quick sketch of what we were looking at on Desmos. Kind of looks like that. And what can we say about this function? What's happening to the current? So we're looking at key terms like increasing and decreasing. What would you say is happening? Is this thing increasing or decreasing? Is it going up or going down? It's increasing, okay? It's increasing over t belongs to the set of real numbers such that t is greater than 0. It's increasing over the whole domain. Is it increasing faster and faster or slower and slower? Slower and slower. So we can say the rate of increase is decreasing. So the function is not decreasing, but the rate at which the function is increasing is decreasing. It's growing slower and slower. Okay? Okay, for 3.5, our practice problems are from page 196. They are numbers 1 through 11.